Hello, everyone. Thank you, Anjana, for the introduction. It's a real pleasure to be here again. If the title of my talk is a bit misleading, we're not going to talk about actual beds and mattresses today. Instead, we will focus on software complexity and looking at it from different angles, and see how we can manage complexity in an ever-increasing code or day-to-day code. Sorry, I just need to grab my water. I got a bit too fast on the stage, and it's already happening to me. Sorry about that.
On brand. Water.
Yeah. OK. A bit short disclaimer. My talk contains light animations and transitions, but no sounds besides my voice, and no flashing content. So if you have photosensitivity, it's pretty safe to watch this. As Anjana said, my name is Andrei Pfeiffer. I come from Timișoara, which is a very large city in the west part of Romania, which, by the way, this year is the European Capital of Culture. So it might be worth to pay it a visit this year. I currently work as a co-designer for Smile Cloud Biometrics, a local product company that is focused on cloud-based, cutting-edge dental solutions. I'm also highly involved in the JavaScript community, being the organizer of Team.js, which is the local JavaScript meetup in Timișoara, and which, by the way, next month in June will celebrate its 10th anniversary. And we are thank you. We are in close relationship and friendship with the community here in Cluj. Now, if culture alone is not a reason for you to visit Timișoara this year, I have another invitation for you. Let's rethink, revisit, and revolve the JavaScript ecosystem and its practices at Revo.js, which is a community-driven conference which will take place this October in Timișoara. We basically share the same values as JSHeroes. The Revo.js is highly inspired by this conference, and you can say it's the sister event that takes place in the second half of the year. So tickets are already up for sale, and we are still looking for 7 more speakers to fill in our agenda. So please check out the website, apply for the call for speakers, and hopefully we'll see each other in October in Timișoara. OK. Let's go back to WaterBeds. Did anyone in the audience ever had a waterbed? Nobody? Wow, thank you, because I never had one. So I didn't know how to draw it, like coming after Jeff, you know. Just imagine that this is a waterbed. Now, as far as I read, waterbeds are just like regular beds, but their mattress is filled with water. Now, the particular thing about waterbeds is that when we apply pressure on one side, the water will move to the other side. And if we move the pressure point in the opposite direction, well, the same thing will happen in a mirror. This happens because water cannot be easily compressed. We know that from physics. So whenever we push it down, it has to travel somewhere else. Now, based on this observation, Larry Wall coined the waterbed theory back in, well, I don't know exactly the year. And it states that some systems contain a minimum amount of complexity. Attempting to push down the complexity in one place will invariably cause it to pop up somewhere else. Now, the same idea can be found in the law of conservation of complexity, also known as the Tesler's law. And Larry Tesler said that every application has an inherent amount of complexity which cannot be removed or hidden. Instead, it must be dealt with, either in product development or in user interaction. Now, let's focus on the first paragraph for a second. So Larry talks about inherent complexity, but what does it actually mean? Well, we probably heard of the unnecessary complexity that everybody tells us to avoid, right? And Larry doesn't talk about this kind of complexity, and we won't be talking about this as well, how to handle it and how to remove it, because that's a different topic that deserves its own presentation. And this is very different from the inherent complexity. To give an example of how I envision inherent complexity, did it ever happen to you to look at someone else's code and think that wow, this is way too complicated, like there must be an easier way to do this. And you start rewriting it, re-implementing it, coming with your better solution, and at the end, you end up with the same, more or less the same complicated code. That's basically the inherent complexity that you cannot easily remove or hide away. And this happens for a bunch of different reasons, like the factors that generally increase complexity of our code are very many. Some of the most important ones, I would say, are dependencies, either first-party or third-party, control flow statements like if, switch, that branch our code, or iterations using for or while loops. User input, collecting through forms, or state that changes over time. And this list is not comprehensive, like there are many more factors, but I think these are the important ones. And we as developers don't write these complexity-increasing statements just for fun, right? We write them because we need to implement requirements. So you could say that complexity, generally speaking, is merely and simply a consequence of business needs. And we need to implement and to write this complex stuff, because otherwise we will get like useless and basic products that are not that useful for us. So getting back to Tesler's law, it talks about inherent complexity that cannot be removed or hidden. Instead, someone has to deal with it, either in product development or in user interaction. Now, there are many examples about this kind of behavior. Like all the speakers that presented before me touched upon this specific detail in more or less. But I would like to go through an example that all of us use on a daily basis. This is the copy, cut, and paste functionality, which, as a side note, was invented by Tesler himself, when he basically figured out that he had to duplicate or replicate content, existing content in some parts of his application, and to replicate it into other parts of his application. So he did a lot of manual effort in order to duplicate this content, so he pushed the complexity from the consumer to the implementation itself, to the program. Now, from my own experience, this behavior is not limited to user interfaces and product development. Instead, it can be, I found it, everywhere there is an interface between some provider, which hides away some complexity, and a bunch of consumers that would like to consume and to use whatever the provider provides. So today I would like to expand Tesler's law and state that every reusable code has an inherent amount of complexity which cannot be removed or hidden. Instead, it must be dealt with either in the implementation or by its consumers. So, to prove my point, let's take an example of a UI component which changes and evolves over time as requirements change. Now, for the sake of this example, I will use React and TypeScript, but you can, the theory applies to any UI framework and to any programming language. Instead, it's not even limited to UI components. It can be applied to small code details like every reusable function or class, or to higher and larger pieces of code like a library or reusable library or a RESTful API, for instance. So let's take this, our item component. It just displays some text in the UI that is received through the body input. Below the dotted line, you see the consumer part of the component, how the component is actually used. Above the dotted line, we see the authoring part, the implementation of the component. It exposes an interface, which for the beginning, it only includes a single prop, the body, which is a string. Now, we don't particularly care about the actual implementation, but you can imagine that it will encapsulate some styling for the time being. So let's go on and add some new requirements. So from design, we get a new requirement that forces us to support a new use case, like an arrow item, a common pattern in UI in mobile UIs, hinting that we can navigate to another screen. Now we need to add a new prop in this regard. We'll call it an arrow, give it a type Boolean. And you can imagine that in the implementation, we would have to probably import an icon component, apply the proper styling, and conditionally rendering it in the UI if the prop is passed from the consumers. But the consumers don't know and don't care about any such details, right? Everything is hidden away in the implementation. Now, after a while, we get a new requirement, like we have to support a check mark or a checked icon, a checked item. Now, we could add a new prop, but that probably, I would argue that is not such an elegant solution. So let's refactor our code and change the arrow, the Boolean arrow, with another prop, let's call it icon, that can receive two values, an arrow or a check. And based on whatever the consumer passes into the component, in the implementation, we will conditionally render one icon or the other with the proper styling. Great. But after a while, we get a new requirement. We need to display some sort of amount inside a blue bubble shape. Unfortunately, we cannot reuse the icon prop, right? So we'll have to add a new one. Let's call it count, give it a type number, and whenever the consumers pass in that particular prop, we will probably import another component, like a badge, for instance, for the blue bubble shape, apply the proper styling, give it the background color, the text color, and conditionally rendering in the UI. Now, the examples can go on and on forever, because we know that in real-life applications, this list will get longer and additional features will need to be added. But for the sake of this presentation, let's stop here, OK? Now, taking a step back and looking at our implementation, we can say that this is a complex implementation because all the complexity, or most of the complexity, is hidden away inside the implementation. Looking at the consumers, it's easy for them to use the component because they only need to pass in the proper props, the proper inputs, and everything gets handled by the component itself. But the downside is that they also lack control, and they lack the customization control. So whenever they need to change the requirements or need to support new use cases, someone has to build that into the implementation. Like the consumers only can use whatever is exposed to them. So let's look at another approach, how we can move the control or to inverse the control from the implementation to the consumer. It's a common pattern. It's called inversion of control. So basically pushing the control the other way around. So we could replace all our optional props with a single prop, let's call it extra, that can receive any arbitrary UI component. In our case, a React node, because the examples include React. Now, the implementation is really dumb and simple. It doesn't know what it will render, and it doesn't care what it will render, because the consumers are in control. They can basically pass in anything they want. But now, also, the complexity moved from the implementation to the consumers. The consumers need to import the icons. They need to apply the proper styling. So everything, can you see like the WaterBed theory in action, like pushing the water from one part to the other? Now, let's take another step back and look at the two implementations side by side, or one below the other. So we have our first implementation was complex. Everything was embedded and hidden away in the implementation. For the consumers, it was easy to use, but it lacked the customization control. This is, by the way, great for reusability. So whenever we have to restrict our consumers in order to only use a specific set of use cases, or they don't need customization control, then this approach is very viable. Now, on the other hand, we tried the simple implementation where we moved the complexity from the implementation to the consumers. The implementation was fairly simple and dumb. The consumers could customize everything, whatever they want, but they also had to take care of the complexity of importing components, importing dependencies, and apply the proper styling. This is great for customization, right? Whenever we have many consumers that each of them needs to, I don't know, provide a use case or a particular customization, this is a great choice in this regard. Now, from my own experience in application development, we rarely use or need one or the other. So we usually need a combination of both, right? We have some consumers that require to easily reuse existing implementation for existing use cases, and other consumers that require customization control. So how can we get the best of both worlds? Well, one idea is to merge the two interfaces together and basically get a really powerful component with all the complexity embedded inside, but also allowing easy customization for the consumers. This is, by the way, a pattern that most UI libraries out there, UI component libraries, use because, yeah, they encapsulate a bunch of functionality, but also allows the user, the consumers, to customize particular things. But in this regard, we only increased the overall complexity of our component. We added more stuff inside. So can we do something in this regard, like to, I don't know, simplify it, handling this ever-growing complexity that will happen inside this component? Well, in our particular use case, the optional props are mutually exclusive, so we won't be using multiple props at the same time. So this is a great opportunity to segregate the interface. Segregation is a bad word, generally speaking, but in computer and in software development, it's pretty good. So we can split this component into 3 different components, have a base component that is the simple implementation that we talked about previously. It doesn't know what it renders, but it's great for customization. And on top of it, we can compose it into other more specialized and more complex components. For example, an icon item, which only encapsulates the icon use case of, that we have to support. And we can also build another count item that only encapsulates the mount use case or the count use case that we've seen previously. So having this implementation, these segregated interfaces, allows us to, one, easily reuse existing specialized components, like the icon item and the count item. We have customization control using the base item. And we could argue that it's easier to maintain when compared to the previous super component with, that can also embed the whole use cases and also allows customization. We basically split the complexity. It's not in one file, it's now in 3 different files. But has the complexity, the inherent complexity, actually changed? Well, if you recall, basically complexity is driven by the requirements. And we still didn't change the requirements. We implemented the same requirements, but in different ways, right? We moved complexity from one side to the other, mix it together, and then split it together in different files. So nothing actually changed, because these are the requirements. Like, we need to support these 3 use cases. And that's the thing with design patterns and software engineering principles. They cannot remove the inherent complexity. They can only help us to manage it. They can remove the unnecessary complexity. Yes, that can be, they can achieve that, but they cannot do anything about removing the inherent complexity that Larry Tesler talks about. How can we remove the complexity? Well, we need to remove the requirement in the first place, and then we can get rid of the code that implements that complexity, right? And this is probably why it is so important to write code that's easy to remove and to identify those use cases that are no longer used in our applications and just remove the code altogether, because that's the only way to reduce the complexity of our programs. So, to conclude, complexity is inherent, like we cannot run away from it. And if we choose not to deal with it, either as consumers or as authors, someone else will inevitably deal with it in one way or another. And remember that complexity, or dealing with complexity, also adds the benefit of providing control over the task that we are trying to achieve. Sometimes we need this control, sometimes we don't. And we as developers are both consumers and authors of code, sometimes changing these two different hats multiple times during the course of a single day. Now, as consumers, sometimes we need to reuse whatever is already implemented, or use cases that are implemented. Other times, we require customization control. And as authors, we need to understand the consumer's needs in order to make educated decisions regarding where should we place the complexity with the control as well. Should we hide them away in the implementation, or should we pass them to our consumers? That being said, I'm very curious about whether you encountered a situation in the past where you have had to move partially or completely the complexity from the consumer to the implementation, or vice versa. It doesn't matter. So yeah, feel free to find me during the breaks. I'll be here for the end of the conference. Thank you, JSHeroes, for having me. Thank you for listening, and please, yeah, do enjoy the rest of the conference. I'm very bad at ending talks.